Hello, everybody. So what we're going to be looking at today is section 9.3 from your book, part 2, power reducing formulas. Now, in the previous video, we did look at this a little bit at the end, but I wanted to make another video with more sample problems and that kind of stuff. Um, Also, you'll notice that this whole thing is written, which is unusual. That's because I'm recording this video for the second or third time because the audio on my microphone cut out in the middle last time. So there's a video on YouTube with no audio on it, or audio for 15 minutes and then no audio for 45. So rather than rewrite all this, I'm just going to go over it. Um, I think that'll be faster anyway, which is probably a good thing. Um, so we'll go to a computer at various points, I think, while we're doing this. And I mean a computer, I mean like Wolfram Alpha or something to show you certain things. But with that said, let's go ahead and get started. Section 9.3 actually covers several types of trigonometric identities. So it covers the double angle formulas, which are here, the power reduction formulas, which are here. This is mostly what we're talking about today, and the half angle formulas, which are here. Okay, and so you want to have these all written down. If you don't, you should get a copy of them from the what's it called? From the handouts page on Canvas, which I'll just show you right now. So let me just log in here. Let us pick our class once it shows up for one of these. Go modules, hit student view because why not? And if you scroll down here, you'll see links to handouts in quite a few different weeks, but it's always the same page. So on the handouts page, you grab the handouts. And there's a unit circle, which is useful to have, and also the trig sheet reduced PDF. And so that's the one you want, is this one. Let's just open it. And you've got lots and lots of identities and stuff here. So for example, I can't actually point on this so you can see, but on the upper right, you have the half angle formulas, and where it says alternate form, those are the power reducing formulas. So they're not called power reducing on the cheat sheet, but it's the same formulas. And all the others that we have are here as well. Double angles there, sum to product, product to sum, etc. So this is a good reference for all of those. And in addition to other things that you would need to know, like the basic stuff from the definition of the unit circle and so on. So that's why we like this. There's a second page with a unit circle and some other stuff. And this one cheat sheet has most of what you're supposed to learn in this entire class. So, feel free to use that. It's very helpful. Let us go back to the notes. All right. So get that cheat sheet, and then you can have a reference for all of this stuff. So let's talk about them. So first thing we want to talk about is where do the formulas come from? And where they come from for the power reducing formulas is they come from the half angle formulas. Yeah, also from the double angle formulas. So here's an example of where you get the power reducing formulas from. So you start with this formula. This formula right here is a double angle formula. Cosine 2 theta equals 1 minus 2 sine squared theta. So you can find that up here in the double angle formulas. It's all these middle ones, right? Cosine 2 theta is 1 minus 2 sine squared theta. Also, cosine 2 theta is 2 cosine squared theta minus 1. So basically one of these has a sine, one of them has a cosine. And that's where you're going to get the two formulas from for sine and cosine. This first one we don't use for this. but these second two are useful. So you start out with one of these, in this case, the middle one from the double angle formulas. And if you take this and you just use regular algebra to solve for sine squared. So if you take this and you're trying to solve for sine squared, you have minus 2 sine squared on this side. So if I want to make it positive, one way to do that is just to add this to the other side. So I do plus 2 sine squared theta plus 2 sine squared theta. I end up with this. 2 sine squared theta is 2 sine squared theta plus cosine 2 theta equals 1, right? Just by moving this over to the other side. Keep your eye on the prize. We're trying to solve for sine squared because I said so. So if you're trying to solve for sine squared, then this cosine 2 theta is extra, needs to be moved to the other side. So we subtract cosine 2 theta from both sides. At this point, it says 2 sine squared theta equals 1 minus cosine 2 theta. So we just rearranged the original formula here, right? Like basically we just took this, solve it for sine squared theta, or in this case 2 sine squared theta. We ended up here. Then you divide by 2. So you just divide by 2, divide by 2. And then you end up here. Sine squared theta is 1 minus 2 theta cosine 2 theta over 2. You can write it that way, or you can write it this way. And you just use whichever form of this you want. And that is the power reducing formula. So if you look up your power reduction formulas for sine squared, it will be this or this. Right, there it is. So you can do the exact same thing to get a formula for cosine squared. The only difference is going to be a plus sign versus a minus sign here. And that's from the original formula here. So cosine 2 theta 1 minus 2 sine squared theta, or cosine 2 theta 2 cosine squared theta minus 1. These two look the same. The difference between them is sine squared, cosine squared, and also the signs are backwards, right? Like this is a minus, this is a plus, this is a plus, this is a minus. So that's why when you solve this middle one for sine, or you solve the bottom one for cosine, you end up with these formulas that look the same, but the signs are opposite. Okay. And then in order to get this last one, tangent squared theta, what you do is you divide these. I can just do it right here. So like if you wanted tangent squared theta, it would be sine squared theta over cosine squared theta, which is, so sine squared theta is 1 plus cosine 2 theta over 2 over cosine squared, which is, I wrote that wrong. This one's a minus. This one's a plus. And then what happens there is your 2's cancel, and you end up with 1 minus cosine 2 theta over 1 plus cosine 2 theta, which is this last formula. So you derive these two, and then you can calculate the third one. You don't have to know the derivations for those. You just need to be able to use the formulas. So let us come down here and say that's where they come from. Okay, so you do this work. You've come up with the power reduction formulas, and then what are we going to use them for? Okay, and so the most common thing you're going to use them for is for, well, it says what it does. It reduces the powers, right? So when you've got a power like this, here's an example. Write cosine squared 7x with only first powers of sine and cosine. I didn't write that, but only first powers of sine and cosine. Okay, so basically what we're saying is that we don't want this because of this second power. So we need to reduce that power somehow. Okay, and that's what you use the power reducing formulas for. So the way you would do it is you say, okay, well, how do we reduce the power on this? Well, you first of all know your formula. here's the formula. This is what we just came up with up here. Well, this one's sine, but this is the one for cosine. And in order to use these, I really want to kind of make a point of this, which I'm erasing it, but I'm going to write it again. So this is your basic, this is your formula, right? This is what you're supposed to know. Power reducing formula. You look this up, okay? And what I want you to notice about this formula here is that this is theta, and this is 2 theta. And the relationship between theta and 2 theta is that this is smaller and this is larger. And the reason I want you to do that, to think of it that way, is because when you're using these formulas, you're either going to be multiplying something by 2 or dividing it by something by 2. And if you are having trouble remembering which is which, just think about what should be smaller and what should be larger, and then you won't get it backwards. Okay, so let's try to apply this here. So if I'm trying to use this identity on cosine squared 7x, what you do is you just copy the form of this. So I would just say like this, like for example, let's do this one. So what you would do is you say, okay, I'm trying to use the identity here. So cosine squared theta is this. So cosine squared 7x is going to be the same thing. So you just go 1/2 1 plus cosine something, right? So that's where I start. And then I have to think about what goes right here, okay? And that's why you want to think about smaller and larger, because you can look at this and you can say like, okay, well, this one's the small angle, this one's the large angle. So if this one's 7x, this one needs to be bigger, right? This is small, this is big. And you know you're either multiplying by 2 or dividing by 2. So in this case, to make it bigger, you're going to multiply by 2, and this is going to be 14x, right? So the relationship is they differ by a factor of 2, but this one's larger, this one's smaller. So small, large. Okay, and that's what we were supposed to do here, because this on the left-hand side, what we started with had a second power, and on the right-hand side, there's no second powers, right? Everything is first power. And that was what the problem wanted you to do. Okay, so no exponent, that's what I wanted. Okay, now that was just a simple example. That's not what the book questions are a little bit harder. So we're going to look at some book questions, okay? So let's go ahead and do that. So here's one straight from the book, not from the book. This is from the homework. So straight from the homework. It's the same type of problem, but they gave me 16 sine to the 4th t. And what it said was basically what I said on the previous problem. I didn't write it here, but basically you have to write with no exponents above 1. Okay, so that's what you're trying to do here. So that just means using these identities. Okay, so let me erase this. And let's look at it a little bit. So the first thing you have to know is this. So the identity that you have, so this is the power reducing formula you're going to use. It only works when you have sine squared, right? Sine squared. This is sine to the 4th. So this does not match this. So you can't just use the identity here and write out the answer. Okay, you've got to do some extra work to make the powers work out. So what you do is you write this 16 sine to the 4th t as 16, oops. And then instead of sine to the 4th, you can say, well, sine to the 4th is actually a sine squared. You can do that. Or if you want, you can think of it this way, sine squared, because when you multiply these two things, you add the exponent. So 2 plus 2 is 4, right? So you have to do that first because you have to be able to see the sine squared in order to use the formula for sine squared. Okay. Now, having done that, then we just want to use the formula here that we used before. Okay, and it's the same exact kind of concept as the previous one. Um, I keep the 16, the square here, the square here, but in the middle I've got sine squared t, and so I've got sine squared t. So this is going to be whatever sine squared t is, and then we just copy the formula from this formula. So what would we do for sine squared t? Well, it would be equal to the right-hand side here, 1/2 parentheses 1 minus cosine 2 theta, but it's 2 theta when this is a theta. When this is a t, it should be 2t, right? So we just apply the power reducing formula here. Okay. Now, you might think you're done here because we were done after this step on the previous problem, but you're not. You're not done on this step because even though this is cosine to the first, and we're trying to write with no exponents above 1, there really is an exponent, like there really is a cosine squared here, right? Because this entire thing is squared. So at some point, the cosine is going to be squared. So this is not actually a 1 exponent, even though it looks like it because of this power 2 here. Okay, so we're not done because the cosine is still squared. So what do we do? Well, what you have to do is actually multiply all of this nonsense out. It's a little bit tedious, but you have to do it. So first thing to do is say, okay, well, 16, fine. 16 is 16. You have 1/2, but it's squared, so 1/2 squared. And then you have parentheses 1 minus cosine 2t squared. So parentheses 1 minus cosine 2t squared. So basically all I did here is I just took out this 1/2 squared just to get it out of the way. Okay, so that's all you do on that line. Then what I want to do is I need to start combining these constants at some point. So I did 1/2 squared. 1/2 squared is 1/4, just to get that kind of out of the way. And then in here, you have 1 minus cosine 2t squared, and you just have to multiply that out. There's not really like another way around it. So, I mean, I wrote it out here, but we'll just do it. So like if you have 1 minus cosine 2t, I shouldn't use these colors. Let me change it. 1 minus cosine 2t like this, you would have to FOIL it out, right? That's what this squared means, is 1 minus cosine 2t, 1 minus cosine 2t. So you'd have to like FOIL this out, right? So you have to multiply the first things and get 1. You've got to multiply the outer. So you're going to have 1 negative cosine 2t, so minus, wait, hold on, is this right? Yeah, okay. Minus cosine 2t. Then you've got the inner 2, which is this and this. So negative cosine 2t times 1 is another negative cosine 2t. And then finally, you've got negative cosine 2t, negative cosine 2t, multiplied will be plus cosine squared 2t. And then you can combine these two terms and you get 1 minus 2 cosine 2t plus cosine squared 2t. And that's not your answer, but that's what you get just when you multiply these out. So we do that. So we got 1 minus cosine 2t squared. FOIL it, you get this. 1 minus 2 cosine 2t plus cosine squared 2t. All right. Then what? Well, the 16 and the 1/4 can just be combined. 16 times 1/4 is 4. Um, I just rewrote this, and we end up here. 4 times 1 minus 2 cosine 2t plus cosine squared 2t. Now you can see the cosine squared that I was talking about when I said we're not done because the cosine is still squared. There it is. So you get to this point right here, and this needs the identity again. So what you have to do is you just rewrite everything. Hey, okay. Um, so this cosine squared is not allowed in our answer. So we have to use the identity again. So 4, bring it down, right? 4, 1 minus 2 cosine 2t, all that part's fine. So 4, 1 minus 2 cosine 2t, that's fine. And then you've got plus cosine squared 2t. So you use the identity here. So you go look up the identity for cosine, and we've already seen it, right? It was 1/2 1 plus cosine 2t. But remember how these work. When you go from uh, this side to this side, the angle doubles and you get the bigger angle right here. So when we're doing this, if the angle started out 2t, it's going to be 4t here, right? Just like on that first example we did, on the first example we did up here, right? When we started with a 7x, we ended up with 14x. So if you start with a 2t, you're going to end up with a 4t here. At that point, we just want to multiply this 4 through on everything. So 4 times 1 is 4. 4 times minus 2 is minus 8. 4 times 1/2 is 2. And then this is still in parentheses. Then this 2 can be multiplied by everything. So 2 times 1 is 2. And 2 times cosine 4t is 2 cosine 4t. And then you can combine that 2 here, which is just a number, with this 4, which is just a number, and you get this for your final answer. And so this is what you would actually have to type into the computer, to get credit for that problem. So you got to multiply that all out. It's kind of hard to get Wolfram Alpha to do this. So you can't just type in generally this and expect Wolfram Alpha to know that you would get that you want this. So it's hard to use Wolfram Alpha for this. Okay. So here's another one. This is also straight from the homework. So they're going to go 32 sine squared cosine squared. Okay. And so I think what I did here was I changed my mind to what form of the identity to use. So let's cross that all out. So if you're going to do this one, you got a sine squared. There's an identity. You've got a cosine squared. That's an identity. And we used the form that looked like this. Sine squared, I'll put theta, was 1 minus cosine 2 theta over 2. And for cosine squared theta is 1 plus cosine 2 theta over 2. Basically, you're just changing where we write the 2 on the denominator, right? Like here, I put 1/2, but that's the same thing as just putting over 2. That's just kind of personal preference. Okay, right. Oh, here I wrote it here as well. This and this are the same. So on this problem with sine squared and cosine squared, then I just use the identity twice. And the only thing I did wrong here was you'll see I put 2t and 2t, but actually these were alphas, so it should be 2 alpha. And then what I did is, so I used the identity twice. And then from here, I got a 2 in the denominator and a 2 in the denominator. I moved those 2's out here. So you started with the 32, and then you got 2 and 2 in the denominator. Then you've got this. Just like the previous problem, you can multiply this out. So 32 over 4 is 8, but then you've got 1 minus cosine 2t, 1 plus cosine 2t. That needs to be FOILed out again, just like we did here, but this was minus and minus. This one's minus and plus. So you FOIL this out, just like before. Because of the difference in the signs, actually these middle terms end up canceling each other out. And you're only left with this. 8, 1 minus cosine squared 2 alpha. You multiply this 8 through, actually, I guess you don't. 8, 1 minus cosine squared 2 alpha, but this is a cosine squared again. You're not allowed to have a cosine squared. You need to use the identity again. So you look up the identity for cosine squared. Here it is, right? Just like every time we've done this, the angle doubles. So 2 alpha to 4 alpha when you apply this identity. From here, everything just needs to be kind of multiplied out. So in this case, 1 plus cosine 4 alpha over 2, I distributed the 2, 1/2 plus 1/2 cosine 4 alpha. This minus is on everything. So you have minus 1/2, minus 1/2, minus 1/2 cosine, minus 1/2 cosine 4 alpha. Once you multiply that out, this 8 that was on the outside can be distributed on everything. 8 times 1 is 8. 8 times 1/2 is 4. 8 times 1/2 is 4. And you get this. Combine the 8 and the 4. 8 minus 4 is 4. And you end up here. And this is what the computer wanted. This is the answer. Okay. And that's how they go. Now, I know that these kind of are long at first, but you should also notice that they're really the same problem over and over again. Okay. So once you become comfortable with this idea that like apply the identity, multiply everything out. Oh, you have another square. So you need to use the identity again. That's kind of the key on these. That happens over and over. All right. Bonus half angle example. Okay. So this is these are problems that are just like also in the homework that I thought maybe people would want to see. So this is just more examples. Okay. So here's another type of question straight from the homework. So what they're doing is they say this. They say sine theta, They say sine theta is negative 24 over 25. Okay, they just give you a piece of information. They say theta is in quadrant 3. You need to know that. And then they say, what is tangent theta over 2? Okay, so if this is what you're being given, then what you need to do is you say, okay, well, what am I being asked to calculate? Tangent theta over 2. Can I find an identity for tangent theta over 2 to relate it to theta? So you look at your list of identities up at the top. So we're looking for tangent theta over 2. So you look here. No, this isn't right. This isn't right. This one's right. Okay. And so, I mean, this is alpha over 2, but, alpha, theta, who cares? So you get these. Now, these formulas, by the way, are just the same as the ones up here. Just if you square root both sides, square root both sides, square root both sides, you end up with these square roots. Now, something about the half angle formulas, though, that's kind of annoying is this plus or minus business that's on these three. And I'll show you what to do there, but not on this problem. I'm going to redo this problem. What you want to notice here is that for tangent's special because there's 3 different formulas. And so what this means that there's 3 of them is that you can actually pick which one you want to use. Okay, so since tan alpha over 2 is equal to all 3 of these, you can choose the one you want to use. Okay, and the plus or minus is annoying, so I would probably use one of these two for the problem that we're going to do. So let's actually do that. So let's use this one maybe. Let's use tangent alpha over 2 is equal to, let's go sine alpha, I guess it doesn't matter, over 1 plus cosine alpha. This is the one we're going to use. Okay, duplicate. So we're going to go down to the problem that we were going to solve. It's going slow because it's zoomed in. All right, cool. So let us put this here. Now, get that out of the way. Okay, so here's what I wrote when I did this the first time. I said, we need an identity for tangent theta over 2, and I picked the one with the plus minus. Okay, and let's look at how long it took me to solve it. We're not going to solve it this way, but I needed to know cosine theta because that was in the formula, and I needed to know whether the answer should be plus or minus because of the plus or minus. And I did this work. Look at all that work. Right? So that's a lot of work. So we didn't like that. So we would like a better way to solve this. So if I do solve this with this better way, we'll use the identity that I have right here. So I have to delete all this. Hold on. Scribble, scribble, scribble. Okay. More scribble. More scribble. We'll just scribble when we get down to this, I think. Okay. We're almost done. Okay, we're almost done. What? Why didn't you erase all the stuff? Okay, we're done. All right, so let's do this. So, can I make this bigger? I wonder. No, I can't. Okay, so we need an identity for tangent theta over 2. We're going to use this one. Tangent alpha over 2 is sine alpha plus, or over 1 plus cosine alpha. Okay, now look at the information we have. So this is what you should think when you look at this. You should think, so we're going to use our formula is this one. I'm going to write it with theta this time. Theta over 2 is sine theta over 1 plus cosine theta, right? Now, in order to use this, I need a sine theta and a cosine theta. So we need to know sine theta and cosine theta. Okay? We already know sine theta. We already know sine theta because that was just what they gave us in the problem, right? Sine theta is negative 24 over 25. Okay, so what do we need? We need to calculate cosine theta. So what we need to do is, number one, we need to calculate cosine theta because we don't have it right now. And after that, then we can calculate tangent theta over 2 using our formula. Okay, so those are our steps to this problem. Okay, um, so let's do that. Let's calculate cosine theta first. So to calculate cosine given the sine, we'll use a trig identity. So to calculate cosine theta when given sine theta, we use this identity. Sine squared theta plus cosine squared theta equals 1, right? That's the Pythagorean identity. Okay, so all we're going to do is, oh, I wrote this stupid up here, I just realized. Um, this is negative 24 over 25. I wrote negative 24 over cos. That makes no sense. Okay, sorry. All right, so you use this identity here. Then they told us sine theta is negative 24 over 25. So we're going to put the negative 24 over 25 into the sine, right? So this right here is going to go in here. So you do that, sine squared. So this is squared. So it's negative 24 over 25 squared. And then you've got the rest of this plus cosine squared theta equals 1. So this right here, negative 24 over 25 squared, you actually work out. So I have to grab a calculator and I just do 24 over 25 squared. And this needs to be exact, no decimals here, okay? So 576 over 625. So exact, no decimal. Okay, that's important. And then we got cosine squared theta equals 1. So if you don't have a calculator that can do fractions, then that's where you would just come over to Wolfram Alpha or something. And, you just type in negative 24 over 25 parentheses squared, right? So that's all you have to do to get the answer. Of course, I could actually hit enter on that and get a more in-depth answer. Not that we need it. Take your time. I mean, that's all there is to it. So if your calculator gave you this 0.9216 answer down here, you can't see that, but over there, if you get this negative 9216, that's not what you want. You want the 576 over 625. Okay, so make sure you get the exact answer there. And now we're trying to solve for cosine. So you've got to solve this for cosine. So you need to subtract this 576 over 625 from both sides. On the left-hand side, you're just going to end up with cosine squared theta. On the right-hand side, you have 1 minus 576 over 625. That's another job for a calculator. That's why I left this up. 1 minus 576 over 625. So 49 over 625. Like that. And then here, you need to square root both sides. So you square root both sides, you get cosine theta is going to be plus or minus 49 over 625, which you do that on a calculator as well and get an exact answer. I know that the square root of 49 is 7, and the square root of 625 is 25, which I normally may not know, but I only know it because I just did 25 squared to get 625, so I remember it. But you can use a calculator. Okay, now from here though, what about the plus or minus? So on these problems, you need to be careful here. So you have this plus or minus. It's not both, only one is correct. So you have to know the unit circle in order to get that right. So how are you going to use the unit circle? Well, here's how you would use it. So at the beginning of the problem, they told me that theta is in quadrant 3, right? Theta is in quadrant 3. So that was given, right? This was given to us in quadrant 3. Okay? So if theta is in quadrant 3, right, which is 1, 2, 3, 4. So if you're down here somewhere, right, then your x value is negative, x is less than 0 down here. That's the left half of the graph. And also y is less than 0. And that means that in this quadrant, the sine is less than 0 because that's the y value. The cosine is less than 0 because that's the x value. And the tangent is actually positive because when you do a negative over a negative, you get a positive number. You could also remember these in various ways. Um, yeah, you can remember these in various ways. You can remember that. Um, so for sine theta, cosine theta, tangent theta, in the first quadrant, they are all positive, right? A for all positive. In the second quadrant, only the sine is positive. In the third quadrant, only the tangent is positive out of these three. And in the fourth quadrant, only the cosine is positive. And then they give you kind of an acronym, not an acronym, but to remember this, they put an A here, S here, C here, T here, right? A, S, C, T. Um, Normally there's an acronym like all students. I just got my letters wrong. Tangent, cosine, T, C. Normally they have an acronym like all students take calculus or something, or a something trig student. I can't think of an adjective that starts with a C. Um, but anyway, so you got to know what trig functions are positive in which quadrant. So the point of that is that if theta is in quadrant 3, um, so if theta is in quadrant 3, then what can we say about the cosine? Because we have a cosine right here. The cosine, it could be plus or minus here, but down here, tangent's positive, but the other two are negative. So the cosine must be negative. So cosine is negative. And also just to write it out, sine is also negative. But tangent, by the way, is positive. Okay. And that's how you use that information. So specifically, cosine theta, which we found to be plus or minus 7 over 25, is actually going to be negative 7 over 25. I'm going to write that in a different color. Okay. And just by the way, this is also the same idea as you would have to use if you were going to use this formula, right? because tangent alpha over 2, if you were going to calculate using this um, formula with a plus or minus here, you'd have to say like, oh, okay, well, if theta is in quadrant 3, theta over 2 is where? I think it's quadrant 2. You'd have to look it up. You have to think about it. And then decide whether to use a plus or minus. But so that's how you decide on the sign of things based on the quadrant. Let's finish this off now. So once we have that, now we can use our formula now that we have the cosine. So we know now that sine theta was negative 24 over 25, and cosine theta is now negative 7 over 25. So tangent theta over 2, right? Not just tangent theta. In order to get tangent theta, you would divide these, right? But this is tangent theta over 2. And we use this formula here. Sine theta 1 plus cosine theta. That was the formula that we looked up. So then you just fill in the numbers. So you have sine theta on top, negative 24 over 25. And then on the bottom, 1 plus cosine theta, which is 1 plus negative 7 over 25, which is negative 24 over 25 over negative 18 over 25, which is negative 24 over negative 18, which is, I think 6 goes into both of those. 6 goes into 24 4 times. 6 goes into 18 3 times. So I think that's their answer. Okay, and that's how you do those. And then just one last thing, because I think it's a little bit tricky. So this is just extra here. Suppose theta is in, let me say, quadrant 4. Okay, for example, quadrant 4. And if I say, let's ask about tangent. Should tangent theta over 2 be positive or negative? Right? That's a question. The reason you would need to know that is because, again, if you were using this top formula, you would need to know the plus or minus. Or for these, you would need to know the plus or minus as well. So for any of these 3 formulas, you'd have to do what we're doing here for this last little thing. So just how would you do it? It's not hard to figure out. What you do is you just do it in very systematic way. You say, so just write down some facts. So theta is in quadrant 4. Okay. Now remember where the quadrants are, right? Like just draw a little picture here. 1, 2, 3, 4, right? But think about the degrees: 90, 180, 270, right? 360. That's also 0, but 360. So if theta is in quadrant 4, theta is between 270 and 360, right? 270, 360. Just because you are in here, right? 270, 360. And then if you want to know about theta over 2, divide by 2. So 270 over 2, theta over 2, 360 over 2, you get, just actually divide these, 135, I think, theta over 2, 180, like that. So then you use the unit circle using what we already talked about, right? Like this is 0, 90, 180, 270, and then back to 360. Um, if you're between 135, if you're between 130, that's not what I wanted. If you're between 135 and 180, well, 180 is here. Where's 135? 135 is in between 90 and 180. So it's like right here or something, right? So you're right here. That's where you are. So what quadrant are you in? If you're in between 135 and 180, 135 and 180, you're here. This is quadrant 2. Right? Theta over 2 is in quadrant 2. And then from there, you would be able to use that information to know whether it should be positive or negative. So in quadrant 2, you'd be able to say that sine theta over 2 in quadrant 2 should be positive, but cosine theta over 2 in quadrant 2 should be negative, and tangent theta over 2 in quadrant 2 should also be negative, right? Just based on this information. Quadrant 2 sine's positive, but the others are negative. So that's how you go about that when you have to figure out whether one of these is positive or negative. You've got to go from where theta is, divide by 2 to get where theta over 2 is, and then figure out where that is. Okay, so I think that's it. So I'm going to stop this here and upload this for you guys.